This video is about science, in particular about the role of culture and community in science, how they influence what scientists do, and how they reason. I'm going to start by talking about method. Now, scientists are not the only people who argue that they are pursuing truth. People of religious faith, philosophers, also talk about truth, but they use different methods. What characterizes science and scientists above all is their use of scientific methods. And those methods are characterized by two things. First is evidence, the comparison of theories about the world with evidence about the world, often taken from experiments. The other is the application of reason. The way that scientists combine evidence and reason is what makes them scientists and what has made science so effective. The question is, how is this actually done? One use of reasoning and evidence that is often associated with science is induction. This is the technique of looking at repeated observations, evidence, and forming on the basis of them generalizations. The classic example offered by John Vickers is the idea that all swans that we have seen are white. Based on this evidence, one might conjecture, therefore, all swans are white. This leap in reasoning is induction. The problem is that the conclusions cannot be guaranteed. Perhaps there are swans that aren't white. All it takes is one observation, one black swan, to disprove the theory. And in fact, there are black swans in Australia, which is the point of the example. This account of science as inductive was rejected by the philosopher Karl Popper, who was concerned that people might make claims that things are scientific when in fact they were false. If all you're looking to do is to confirm a theory that you have, it may be easy to find evidence supporting it. But if there's evidence contradicting it, the theory may in fact be false. Popper wanted to rule out pseudosciences and bad science. He argued that scientists should be critics, that they should be constantly looking for flaws with the theories that they came up with. And he also argued that rather than being inductive, science in fact is deductive. Deduction is contrasted with induction, where induction begins with a number of specific examples or pieces of evidence, and from those formulates a general theory or principle. Deduction goes the other way. It begins with some general categories and produces a specific result. Deduction begins with premises or assumptions. It applies to them rules of logic and reasoning to produce conclusions. And these conclusions are irrefutable unless there's a problem with one of the premises. The classic example is the syllogism, all men are mortal. Socrates is a man, those are the premises. Therefore, Socrates is mortal. Socrates must be mortal unless, for some reason, the assumption that all men are mortal is false, or Socrates is not actually a man. Popper argued for falsification. Whereas induction begins with a collection of evidence and proceeds to generate theories, Popper said that scientists do the opposite. They begin with a theory, and they compare it with evidence. But rather than seeking out evidence that would confirm the theory, he said, they seek out evidence that will disprove it. As in the example of the white swans, the theory that all swans are white can be disproved by a single piece of evidence, a single black swan. Popper said, insofar as a scientific statement speaks about reality, it must be falsifiable, and insofar as it is not falsifiable, it does not speak about reality. What distinguishes science from non-science, in Popper's mind, is that science can be tested, and those tests could potentially turn out to fail if the theory doesn't correspond with reality. There are a number of challenges to Popper's characterization of falsification. One of them, the Duhem-Quine thesis, holds that any hypothesis depends on a collection of assumptions and background, and so that when there's a single piece of evidence that may appear to contradict the hypothesis, it's not clear which part of the hypothesis is contradicted. Critics also pointed to a problem of judging which evidence is sufficient to falsify an established theory. Popper himself acknowledged that a single piece of evidence is seldom enough. Science is rife with anomalies, uncertainties, errors, effects of observation and experiment. But then if multiple pieces of evidence are required, how much? Falsification begins to look a little bit like induction. The philosopher Thomas Kuhn examined the history of science and concluded that this model of falsification is wrong. It's not what scientists actually do. He wrote, "No process yet disclosed by the historical study of scientific development at all resembles the methodological stereotype of falsification in direct comparison with nature." This seems a little bit unfair to Popper. On the one hand, there have been decisive experiments in science. On the other, while Popper thinks that he is accurately describing what scientists do from day to day, he is also making an argument about what they should be doing in order to do good science. His argument that scientists need to make theories that are testable is important. Seeking to describe what scientists actually do, Kuhn's answer to the problem of evidence is not an objective rule or a simple comparison with nature, but the judgment of scientists within their communities according to the standards of those communities. In fact, debates around evidence and error and what counts and what doesn't are central to the pursuit of science. Kuhn further says that scientists are seldom critical. Most of the time, they pursue their work on the basis of what has gone before, without questioning it, without trying to falsify it, but rather trying to fill in gaps. Occasionally, however, there arises a situation when there is actually a revolution within science, and this is the topic of his famous book, The Structure of Scientific Revolutions. Central to all of this is Kuhn's idea of a paradigm. A paradigm, as he describes it, is a collection of background assumptions, questions, and what kinds of questions that count within the disciplines, the methods that are used by scientists, and the kinds of answers that count. It can be difficult to recognize the taken-for-granted assumptions that we have about dominant paradigms. It is perhaps easier to highlight them with respect to past paradigms. For example, the old idea that the sun orbits the Earth, which of course was replaced in the Copernican revolution by the understanding that the Earth orbits the sun. This is one of Kuhn's prime examples. Geological catastrophe used to be what geologists felt produced mountain ranges and other large physical features. It wasn't until the understanding of plate tectonics came in the 20th century that geologists recognized that many of these things happened gradually over time. The Newtonian vision of a clockwork universe that dominated physics up until the 20th century is another example. Kuhn described two kinds of science. The first of these is normal science. This is what scientists do almost all of the time. They operate within the bounds of the existing paradigm. Every scientific paradigm has anomalies and puzzles that need to be solved. In fact, for scientists, this is much of the value of a paradigm. They find it worthwhile not only because it explains things, but because it leaves things for them to do. If there were no problems to be solved or addressed, scientists would have nothing to do. However, sometimes there can be a challenge to the dominant paradigm. Perhaps anomalies build up to such an extent there is evidence that doesn't fit, and scientists, or a few scientists, come up with an alternative. Kuhn says that the new paradigm will be incommensurable with the old. That is, that the one cannot be understood in terms of the other. The idea that the Earth orbits the Sun is not a progressive approximation of the idea that the Sun orbits the Earth. It does not fill a gap in that theory. Rather, it replaces a foundation of our understanding of the movement of celestial bodies. Kuhn calls this kind of radical discontinuity a paradigm shift. His book is the origin of that term. Now, for scientists, their main value for a paradigm is not so much that it answers questions or accurately describes reality as that it offers questions for them to answer. So the interests differ between new scientists and established scientists. For established scientists, the new paradigm can be a danger. It can put at risk the research of a lifetime. Whereas for someone new or someone outside the field, that risk doesn't exist. A paradigm that is new may offer new avenues for research and questions to ask. Therefore, Kuhn argues that in most cases new paradigms are introduced by the young and outsiders in a field, whereas the old may simply choose to stick to the paradigm that they have always applied. It may be generational change that is required to finally accomplish a paradigm shift. It may be that Kuhn overstates the case for revolution and paradigm shifts. The changes in science may actually be more gradual than he describes. But what particularly interests me here, in relation to culture, is the role that consensus plays. There is the problem, again, of evidence. If Kuhn is right, and he's not the only person who has made this argument, then ultimately scientific method, scientific reason, does not offer an objective solution to the problem of evidence. In the end, it's something that stands outside of science, that must be addressed by the community of scientists. This is an argument made by Jürgen Habermas, another philosopher, who says that ultimately scientific reason stands on the back of the reason and the communication of a community, and is not itself scientific. This is not to discard the tremendous value of science or the scientific community. It is to emphasize that science is not simply a method, but also the community and the culture that carries it out. And in that case, one of the most fundamental questions of science isn't simply how it is done, but by whom? Who are the scientists who judge what counts as science and what isn't? And this brings me back to the quote by Kuhn with which I began. To understand science, we shall need to know the special characteristics of the groups that create and use it.